You know, in our perfectly connected world, we just expect things to work. We expect every sound to be crystal clear, every phone call to be perfect, every piece of data to arrive intact. But there are these invisible forces at play, these tiny ghosts in the machine that can muddy our audio and corrupt our data. So today, let's pull back the curtain and take a good look at this hidden world of signal interference.
So have you ever been on a phone call and for just a second you hear this faint, ghostly snippet of a totally different conversation? Or maybe you're into audio production and you've noticed this weird bleed between your stereo tracks that just makes the whole mix sound, well, less defined. These aren't just random glitches, folks. They're symptoms of a very specific and honestly, a pretty fascinating problem.
All right, so the villain behind all these issues actually has a name, and it's one that engineers have been battling for, get this, over a century. We are talking about Signal Crosstalk, the unwanted eavesdropper living inside our electronics.
So what is it exactly? Well, to put it simply, crosstalk is when a signal traveling through one wire, or one circuit, decides to bleed over and create an unwanted effect in another nearby circuit. Think of it like being at a loud party. You're trying to hear your friend, but you're also getting this distracting murmur from the group standing right next to you. That's crosstalk.
Now, this isn't some kind of magic, it's just pure physics, and it happens in three main ways. First up, you've got capacitive coupling. This is where the electric fields of two parallel wires interact, causing the signal to basically jump across the gap. Then, there's inductive coupling, where the magnetic field from the current in one wire actually creates a whole new unwanted signal in the wire right next to it. And finally, conductive coupling can happen when two different circuits share a common connection, like a ground wire, which lets noise travel right between them.
But here's where it gets really interesting. This crosstalk, it doesn't act the same way everywhere. It has two totally different faces depending on whether it's haunting an analog system or a digital one. And trust me, understanding that difference is absolutely key.
You can see the big divide right here. In the analog world, crosstalk is that classic thin, tinny bleed-through we talked about. It tends to get worse at higher frequencies, and it can totally mess up your stereo image, making things sound muddy. But in the digital world, oh, it is so much more sinister than just a little noise. It's what we call a signal-dependent error. This means it doesn't just add random static, it actively corrupts the ones and zeros of the data itself. And in doing so, it creates this predictable, but highly undesirable, harmonic distortion.
And look, this is not a new problem by any stretch. As Hugh Robjohns from Sound on Sound points out, analog crosstalk is the classic audio engineering headache. For over 100 years, designers have been trying everything, shielding wires, improving layouts, isolating circuits, all to keep those signals pure and keep those channels separate.
But like we just saw, digital crosstalk is a completely different beast. It's not just a faint copy of another signal making things a little noisy. No, it's a systematic corruption of the data, and its effects can be way harder to diagnose.
So here is the absolute crucial point. When a digital signal, like the switching of ones and zeros, bleeds into an analog path, like inside a data converter, it doesn't just create random hiss. Because those digital bits are directly related to the original signal, the interference they cause creates harmonics. You can think of these like unwanted, distorted echoes of the original frequency. This isn't just static, it's a fundamental change to the very character of the sound or the data.
Okay, so we get it. There are two different kinds of crosstalk. But why does that distinction really matter so much? Well, the impact on everything from immersive 3D audio to high-precision scientific gear is just profound. Let's start with something fun, audio. We all love the idea of true 3D, binaural sound that comes from our speakers, where it feels like you're right there in the middle of the recording. But to actually achieve that amazing effect, you run headfirst into one massive hurdle. The main problem with 3D audio from speakers is actually pretty simple to understand. For the illusion to work, the sound that's meant for your left ear has to only go to your left ear. Same for the right. Now, headphones do this perfectly, right? But with speakers, sound from the left speaker inevitably travels through the air and reaches your right ear, and vice versa. That unwanted signal path, that's acoustic crosstalk, and it completely shatters the 3D illusion.
And the problem gets even more critical when we step away from just listening and into the fundamental building blocks of our technology. See, every single digital device, your phone, your car, a satellite in orbit, it relies on data converters to turn analog reality into digital information and then back again. Digital crosstalk here isn't just a minor annoyance, it's a fundamental source of error.
And this quote from Analog Devices really highlights how serious the consequences are. An engineer might see some harmonic distortion and immediately think an amplifier is failing. But the real culprit could be the digital bits bleeding back into the analog circuit. And if you don't understand that mechanism, trying to fix the problem can be an absolute nightmare, wasting tons of time and money chasing the wrong fix.
Okay, so the problem is clear, both in the analog world and the digital one. How in the world do engineers fight back against this ghost in the machine? Well, they use a really clever combination of strategies to keep our signals clean.
It really all boils down to a two-pronged attack. The first, and honestly the most important, is prevention, just building systems from the ground up to be as resistant to crosstalk as possible. The second is active cancellation, which is a more advanced technique used for situations where prevention just isn't enough.
Prevention is really all about good engineering hygiene. It means using properly shielded cables that contain those electric and magnetic fields. It means physically keeping your power cables away from your sensitive signal cables. Using balanced connections, like the XLR tables you see on microphones, helps cancel out interference. And on a circuit board, it means carefully designing the layout to keep the sensitive analog traces far away from the noisy digital ones. Every single one of these steps is like putting up another barrier against that signal bleed.
But what about that 3D audio problem we talked about? You can't really prevent that. You can't stop sound from traveling through the air. So for that, engineers use an incredibly clever trick: active crosstalk cancellation. The system actually measures the unwanted signal that's bleeding over to the wrong ear, and then it plays an exact inverted copy of it, an anti-crosstalk signal. The two signals meet in the air and poof, they cancel each other out, preserving that amazing 3D effect. It's brilliant. And this all brings us to a final thought. We are constantly pushing to make our electronics smaller, faster, and more powerful than ever before. That means we're cramming more and more circuits closer and closer together, and we're running them at insanely high speeds. In this ever more crowded digital world, the fight against crosstalk, both analog and digital, is more critical than it has ever been. It seems the ghost in the machine is a persistent one, and engineers are going to have to be more vigilant and more clever than ever to keep it at bay.